Today we will see some important points on Cauchy's theorem. Since we have studied the analytic function, harmonic function conditions, all of them will be useful now, and so I was saying that since we have studied them, now we are in a place to go ahead of that and study the Cauchy's theorem and its integral formulas. So that is what we will see here. The one observation which can be derived again, but we will not be going through derivations, but we will simply note down the observation, that what we get from that. And it is that Cauchy-Riemann equations that we studied, the CR equations, in case if you don't remember, then I will write it for you, that del u by del x equals del v by del y and del u by del y equals minus del v by del x. So these were the CR equation we studied, okay, and these CR equations are condition for two real integrals. So now we will start doing complex integrals. So these CR equations are the precise condition for two real integrals, and which are those conditions that we will see now. So the first statement which we are going to note is that the CR equations are precisely the conditions for two real integrals in. So what is the first condition? The first condition is to be independent of path. And that's what we had actually defined earlier when we studied the analytic function. We said that the analytic function is a function for which, whether you move from one point to the another, it doesn't matter that which path you choose to reach, the result should always be the same. And that's how we defined the analytic function. So here also the first condition is the very same which we are aware of, that the integral should be path independent. And second condition is, so basically this is path independent. This means that the function is analytic in the region, and we call that region D. So let me write the details, that the integral should be path independent, and hence the line integral of function f of z which is analytic in the region D is independent of path joining any two points of D. That's what we defined, and we had seen some similar picture when we define the analytic function, that I have a point P which is x, y, and then I have a point Q, this is point Q, and that point is x plus dx and y plus dy. So if I want to, let's say, move from Q to P and remove this delta differences, then I can always have a many ways through which I could reach the desired location from Q to P. I could just come straightly down here, or I could choose any other path. We defined this earlier. I just drawing this to recollect the memory, and this is what we did. So this is the region, and I call it a region D, in which the function, so when this happens, we say that the function is analytic. The more precise word to define the function to be analytic is that it should of course give the same value. So the function is single valued, because if it is path independent, that means that it is single valued, and also its derivative is unique. That's how we define the analytic function. I hope you remember that. So this is the very same condition we are aware of, that the CR equations are the precisely condition for the real integrals, and for real integrals they have to be path independent, right? So if you take a line integral of any function f of z, line integral is defined by, so suppose if I have f of z dz, but if I am taking a line integral, then I will just write a little c below it. This means that C stands for curve. So if I have any curve, and again this is a P point and a Q point, so if I want to show the integration along this curve, so this symbol, the integration, and this small c indicates that this is the line integral, and this is the sign which we will be keep using in future when we will do integrations. So it should be path independent, of course, and joining any 2 points in the region D. Okay, and then the second observation is that the second condition is the extension of Cauchy's theorem. And what is this extension? It says that if we have any function f of z which is analytic in any region defined by any region D, between two simply closed curve. I will draw the figure for this. Let me show you the figure first so that you can imagine it well. So we define some region D in a complex plane. I am drawing this so that you are able to imagine that it is inside the plane. But in future, when we will get used to it, we will no longer be using these axes. That will be understandable. So let's say I have one curve, and these are just like concentric circles, but there is a cut in the circle, and we'll see why I have put the cuts. It will be clear very soon. And I join it like this, and now I think I have made a bigger curve. Let us consider this one. Okay, so this point I call A, B, and please don't, this is a mistake, so please don't consider this line. And we also define the direction in which we are going to integrate. Why do we define that? Because that matters really. Like if I'm showing this direction, then I'll say that I'm doing the integral I'm doing the integration from Q to P. So that the points, the directions are necessary. So here also I can show that these two circles. So first the inner one, I call it a curve C1, I give it a name C1, and then the outer curve is called C. These are just two different names. Inner curve means the earlier I drew this figure, this blue one or red one, but this inner one, okay, or C1 means this much, the blue portion you can see. So this whole ring is a curve C1, and then this outer curve is C, excluding this AB line. The horizontal lines are excluded, just the curve. And C1, for this C1 curve, we say that we move in a clockwise direction. The integral is taken like that. And then, so let's say that we moved here, so we reached B, then we went from B to A, and then A, when we reached A, we went to the outer curve and we moved like this C curve, and then we came back to the point A, and then we went from point A to point B, and then from B to the inner curve. So so now this pattern is completed. So you can see that this is the direction of integration that we are going to use. That you start, let's say you start from B, you move in the clockwise direction for C1 curve, then you reach A, and then you reverse your direction. So basically you are moving anti-clockwise for the C curve, you reach a point A, and then you go from A to B. So this is the direction of integration we are going to use. So here we say, when we were writing the second observation, which was the extension of the Cauchy's theorem, it says that if any function f of z, which is analytic in the region D, and that function is analytic not everywhere, but it is analytic between these two simple closed curves. So now of course you will say that we have a cut here. So how they are the closed curve? Closed curve means this is called the closed curve, and this is called the open curve. So of course here there is an opening at A and B points, but we have to imagine that these openings are very small. So actually the distance between these two horizontal lines are too small to be observed. So they are almost like a closed curve. So you can consider C1 to be a whole closed loop, and then C is also a closed loop. So this is a very, very tiny, very, very minor cut we are making here. So you just can consider it a closed curve. So the function f of z is analytic not everywhere, but it is analytic between simple closed curves C and C1. So it is analytic between these two curves, not everywhere. So what is the region between the two curves? It is this one. So the function is analytic in this region, and that region is called a region D. And if it is the case, then so let me write that if the function f of z is analytic in the region D, and what is this region? This region D is between those two curves. So it is between two simple closed curves C and C1. Then we say that when this happens, okay, when this happens, like the function is analytic only between these two curves, so only in the region between these two curves. So if this is true, then we say that the closed integral, this is the signature of the closed integral, this is the symbol, the closed integral f of z dz at c1, at c. So if you take a closed integral on the c curve, then that will be equal to the closed integral of the same f of z function at c1. So it says that the integral at c and c1, both of them are equal. And this means that if I take it this side, then you note that it is f of z dz minus closed integral of c1 f of z dz, and that is equal to 0. So Cauchy's theorem says that if you have any analytic function f of z and f prime of z, the derivative is continuous at each point within a closed curve, then the integral of f of z dz is 0. Let me explain one more thing before this, that why did I do this and why is it that these two integrals are same. To understand this, we have to first consider this case. You see here that this is the integration in the clockwise direction, and then this is in the anti-clockwise direction. Here we have taken the anti-clockwise direction to be the positive direction. So if you are taking the anti-clockwise direction as a positive, then the clockwise will be the negative. So that is what it means here. So we are taking the addition of these two curves. So basically what we are doing is that let us integrate all the red lines. So if I want to integrate the all red lines, then I have four curves. I have four curves. First is the integration along the path C. So one integration is along C. Then the integration is A to B. Okay. Then, so this is the integral first C. Then I went from A to B. Then along path C1. So along this curve C1, and then from B to A. So this is the full complete integration, B to A. So this is the integration along all the red lines we have drawn. Okay. So what have I done? First I have taken the integration. So if I write it symbolically, then this means that the integration of f of z along C, so this outer one, then the integration was from A to B. So from A to B, f of z dz, plus then this integration is along the curve C1, sorry. So it is f of z dz along C1, and then B to A. F of z dz. Okay, so this finishes the full red lines, the red curves. Now, so this is the total integration, and we want to find out the answer to all of this. So if I add all these four terms, what will be the answer? And the Cauchy's theorem says that the answer will be 0. Why is it so? Here is the statement. It says that, we'll get into this later on, but first we need to know this. It says that if you have f of z function, which is an analytic function, and f prime of z is continuous at each point within and on a closed curve. Let's say that curve is C, then line integral of f of z dz on that curve C will be equal to 0. This is the statement. So let's say that if you have a curve C and you define a function f of z that is analytic, and f prime of z is continuous at each point. So this is a curve C at each point within the curve and on the closed curve. So on the curve itself, if the f prime of z is continuous within and on the curve, then we say that f of z dz at the curve C will be equal to 0. Now if you note here that we have a similar case, that it is analytic, of course, inside this curve and on the curve. So by that it should be 0. The whole answer should be 0 because it is analytic inside the region D. So if you consider the same case, that you see that the function f of z is analytic in this blue area. So it is analytic within this region C and within this region C and on the curve itself. The function is defined between these two regions only. Now you will say that if we consider this C1 curve, then it is not analytic in this region. So how is it possible? Now we have broken the rule. We said that the function the f prime of z should be continuous at each point within and on the circle, within and on the curve. So here it is true that it is continuous within the curve and on the curve, and it is defined the same way here also, but we don't need to get into that. It will always satisfy, we assume that it does satisfy this rule that f prime of z of course will be continuous on the curve and here also on the curve and within the curve, and f of z is analytic also. So this part we have assumed that they are valid, and if that is the case, then all these four integrals should be equal to 0. Okay, and here you see that you move from A to B. So your motion is in this rightward direction, and then you move from B to A, then it is in leftward direction. So of course both of them are of equal magnitude and opposite direction, so they will cut each other. So you see here that this part and this part will blow away, they will cancel each other. This one will be positive and this one will be negative. And here also we say that we define counterclockwise as a positive direction, so clockwise will be the negative direction. Therefore this was the reason that this and this were plus, they were added, but then since this is in the opposite direction, we have taken it minus, and then therefore they have to be equal to 0 as we said from this condition. And if this is 0, if I take it on the other side, of course this integral will be equal. So this is how it is derived. So we have gone in the reverse direction, but main statement is this. So always the Cauchy's equation, always the analytic function whose derivative is continuous at each point within and on the closed curve. If you take the integral of such a function if you take a line integral along the curve C, then it will always give the answer equals 0. And this is very important because we are going to use this condition many times in solving numericals, and I will emphasize, I will make a note of this, that we are using it here so that you will be able to understand that how it is utilized in the numericals. So this is something we need to know. Then after that there is Cauchy's integral formula. Again, if you want, you can go through the derivation, but it is really not required. Just you keep means just you remember the observation, the result itself, and you should know some logics, which I think that is sufficient enough. And I don't think there is nothing more you need to know for exam point of view. So now I will quickly go to the Cauchy's integral formula. Sorry. And this is very simple. We just have to remember the equation. It says that if you have an analytic function f of z, and again it is analytic where within and on the closed curve. So this f of z is analytic within and on the closed curve. Let's say that curve is C, and if A is a point, A is any point within this curve C, then if you want to define the function at this point, so that is if you want to define f of A, if you want to define the function at that point which is within the curve C, then that will always be equal to 1 upon 2 pi I into closed integral of f of z dz upon z minus A. Now this is very important result we have to remember. This we will always be using in solving many numericals. Okay, so this is something we have to remember, and this is called Cauchy's integral formula. Okay, so again it is so you define any closed curve C, and in that closed curve the function is analytic within this closed curve C and on the curve C, and if A is any point within this curve C, then we say, and if we defined the f of A, the A point could be anywhere, it has not to be always at the center, it could be here also. So if this is the A point, again it is within this curve C, so it is the same thing. So wherever your A point is, you want to define a function at that particular point, that is the f of A which is you want to going to define, then that will be equal to 1 over 2 pi I f of z dz divided by z minus A, and you take a closed integral to that, and that will be the answer to this question. This is a very useful formula. Now we can differentiate this both sides, and we get the result that f prime of A, this is also important formula we need to remember, f prime of A will be equal to 1 over 2 pi I closed integral f of z over z minus A. So it is just the same till now. Oh, I thought I have not written dz. Okay, so it is just the same till now. It will be just square here. That is f prime of A. You can derive if you wish. Similarly, f double prime of A will be 1 over 2 pi I, but it is not 1 over like this, it is 2 factorial. So it is 2 factorial over 2 pi I closed integral of f of z over z minus a dz. Here it will be cube. So I think we are seeing a pattern here, and therefore we can derive the generalized formula for nth order derivation of function f of z at point A, and then that will of course be trivial, that it will be n factorial upon 2 pi I f of z dz over z minus a to the power n plus 1. So if we remember this one, then we can find any